We'll start out today's video with reviewing three of the main theorems. First, our extreme value theorem. If f is continuous on the closed interval AB, then there is an absolute max and absolute min. And remember, if we want to find that absolute max and absolute min on the closed interval, we do our first derivative test to find our relative max and mins, or in other words, local maxes and mins, and then also test the endpoints. Whichever one is the largest y value is our absolute max, whichever one is our smallest y value is our absolute min. Rolle's theorem, there's three initial conditions. If f is continuous on the closed interval AB, oops, that should be a squared bracket. Differentiable on the open interval AB, and if f of A equals f of B, then there is a C contained in AB where f prime of C equals 0. So what this is saying is continuous function is differentiable. If your y values of the endpoints are equal, then there must be a point that the derivative will equal 0, meaning that there must be a turning point somewhere in between, or at least a horizontal tangent line. So with Rolle's theorem, you check these three initial conditions, take the derivative, set it equal to 0, solve for x, then just double check, make sure those x values are in fact in your interval. And the mean value theorem, if f is continuous on the closed interval and differentiable on the open interval, then basically your average rate of change has to equal your instantaneous rate of change. And what that means is f of b minus f of a over b minus a must equal your derivative at some point c, provided that c is contained in the open interval AB. So you have your two endpoints, the x's and y's. You do change in y over change in x. Whatever that value is, we then set equal to our derivative and then solve for x. Once you solve for x, check and make sure that value is in your interval. So we're going to look at three examples. First, we're going to review how to find the intervals of increase, decrease, and the maxes and mins. We'll start out, take the derivative. We get 3x squared plus 6x minus 24. Note that this derivative is a polynomial, therefore it's defined everywhere. We'll take the derivative, set it equal to 0. Notice everything is divisible by 3. So we'll divide out of 3, and we'll be left with x squared plus 2x minus 8, which factors into x plus 4 and x minus 2, giving us x equals -4 and x equals 2. So those are the values on our number line. We will pick values in each of our gaps and we'll plug it into our derivative. Now remember, it's usually easiest to plug it in the factored form of the derivative. Let's say I took negative 10 million. When you plug it in the first parenthesis, you get a negative. Second parenthesis, you get a negative. Negative times a negative is a positive. In the middle, take 0. So it'll just be 4 times negative 2, which will give you a negative. And say you took positive 10 million. When you plug it in each of them, you get positive numbers. A positive times a positive is a positive. So at the negative 4, we're going from increase to decrease. At positive 2, from decrease to increase. So to start out our intervals, we are increasing from negative infinity to negative 4. The union of that with 2 to infinity. And we are decreasing from negative 4 to 2. So that takes care of the first part. We've got our intervals of increase, decrease, and now find any local max or mins. So we went from increase to decrease at negative 4, so we'll have a local max at 4 comma something. We'll have to figure out or negative 4 comma something. And we went from decrease to increase at 2, so that will give us a local min at 2 comma something. Because these maxes and mins are points on our actual function, we need to plug it into our actual original function. When we plug negative 4 into our original function, we'll get back a negative 64. We'll get a positive 16 times 3 to give us a positive 48. And negative 4 times negative 24. A negative times a negative is a positive, and we'll end up getting back 96. When you combine those all together, it should end up giving us positive 80. So we'll have negative 4 comma 80 for our max. When we plug in the 2, 2 cubed is 8. 2 squared is 4 times 3 is 12. And then we'll get a negative 48, which altogether will give us negative 28. So our local min is 2 comma negative 28. Next example. Does there exist a function where when x is 0, y is negative 1, when x is 2, y is 4, and your derivative is less than or equal to 2 for all x? Well, because we have these 2 points, and we have a derivative value, we're going to work with the mean value theorem. So we're going to do f of 2 minus f of 0 over 2 minus 0, and we want to know, is it less than or equal to 2? Okay, the reason we want to know if it's less than or equal to 2 is because we want to know if the derivative is going to be less than or equal to 2. We know that change in y over change in x needs to equal the derivative at some point. So if that stays less than or equal to 2, then that could be a possible function. Well, f of 2 we know is 4, minus f of 0, which is negative 1, all over 2 minus 0, less than or equal to 2. Well, this becomes a plus, so we get 5 halves, less than or equal to 2. 5 halves is really 2.5. 2.5 is not less than or equal to 2. So therefore, no, there is no function that can have those two values and still have the derivative be less than or equal to 2 always. Basically, to grow enough from 0 to negative 1 to 2, 4, you would have to have a slope some point bigger than 2. Last example, we've got f of 1 equals 10. They're telling us that our derivative is staying greater than or equal to 2 always, and we're looking at the interval 1 to 4. So this is going to again be a mean value. We know f of 1 is 10. F of 4, we don't know. So we've got f of 4 minus f of 1 over 4 minus 1. We know has to stay greater than or equal to 2 because they told us the derivative is always going to be greater than or equal to 2, and we know that this should equal the derivative at some point. The one that we know is we know f of 1 is 10, so this is really f of 4 minus 10 over 3, because 4 minus 1 is 3, is greater than or equal to 2. And now we'll try and get the f of 4 by itself. By cross multiplying, we'll get f of 4 minus 10 is equal to 6. Add your 10 over, or sorry, not equal to, greater than or equal to. And we'll get f of 4 is greater than or equal to 16 by adding the 10 over. Now remember, this is not your answer. If you just write f of 4 is greater than or equal to 16, you're going to lose a point if this was a quiz or a test. How small can f of 4 possibly be? Well, if f of 4 has to be greater than or equal to 16, the smallest it can be and still satisfy that statement is 16. So the answer would be the smallest that f of 4 could be is, in fact, 16. That's all for today's video. We'll see you next class period.